Okay, I want to conclude with a few words about wormholes and time travel. I think a lecture on what we have learned during my career would not be complete without saying something about this. And I think many in the audience are probably eager to hear what we have learned. So wormhole. Suppose that our universe in the bulk is bent around like this. This is a two-dimensional slice through our universe, like I was doing for the equatorial slice through a black hole. It's bent around so that our solar system over here, and in particular Saturn, is only a distance of a few kilometers away from some galaxy in the very distant universe. So if we travel out through the universe, it may be 10 billion light years to the solar system from there. But across the bulk, it may only be a few kilometers if we can travel across the bulk. But we are three-dimensional beings. We have three space dimensions, two if I've removed one like this. And we can't live in the bulk. The electromagnetic force that's crucial to our existence and our life can't even exist in the bulk, and it can only exist in three space dimensions, two if I've suppressed one like this. And so in order to go across the bulk, we need to have a structure, a wormhole it's called, like that, where you could travel then along the surface of that. The surface looks two-dimensional, it's really three-dimensional, to get from our galaxy to this distant, from our solar system to this distant galaxy. In the movie Interstellar, this is what happens. Bulk beings that live in the bulk have provided to the human beings in this movie that I worked on, have provided to human beings a wormhole of this sort. Eugenie von Tunzelmann at Double Negative in London and a set of painters associated with her made paintings of the center of this galaxy that is on the other side of the wormhole. I worked out the equations for the propagation of light beams from that galaxy through the wormhole up to the camera. I fed them to Oliver James, whom I have mentioned before, who is the chief scientist at Double Negative, and he then programmed those to make a movie that I'm going to show you of what it looks like to go through a wormhole. So this is what the wormhole looks like in the movie Interstellar, for those of you who have seen the movie Interstellar. For the movie, I'm going to move the wormhole up almost in front of Saturn. So Saturn is very far away. The wormhole is only a few kilometers across, and Saturn is very, very far away. And so it looks about the same size as the wormhole. Light rays from the Saturn bend around the wormhole to produce this image, and bend around the wormhole on the other side to produce that image. And if I now start to travel into the wormhole, the images of Saturn are pushed apart as I go into the wormhole. I'm entering the wormhole now. I'm traveling through the wormhole, and I've come out the other side. That's what it really looks like for the wormhole in the movie Interstellar. I had a telephone call from Christopher Nolan, the director of Interstellar, when he first saw this trip through the wormhole. They were in the process of starting to integrate the computer graphics into the film. He had just finished shooting all the human action. He said, "We've got a problem. Would you come over to my house? I want to talk about it." And so I went over and he said, "Look, this is not exciting enough." And we had agreed, I'd happily agreed with him, and he'd agreed with me that we would do everything we could to make all of the movie be scientifically accurate to the extent it did not get in the way of making a great movie. And this is the one place where we compromised, or where we had a significant compromise. So what did I say to him? I said, "You use artistic license." And so that's not the trip you see, though it resembles this, but there's a lot of artistic things stuck on top of it. But this was the real trip through the wormhole. Now, the problem with wormholes is that, as John Wheeler, my PhD advisor, showed back even before I was his student, together with a young colleague, Martin Kruskal, a wormhole will pinch off if you don't do something to hold it open. So if I have a particle of light, a photon, trying to travel through the wormhole to bring me an image, and the wormhole is just empty, sitting there with nothing except, say, a bunch of light traveling through it. Then, as the light travels through, just at the moment that the photon reaches the center of the wormhole, it pinches off, and you're left with two naked singularities, and the light has been destroyed. So you can't get the light through, and you can't get humans through. So there's the issue of how can you hold a wormhole open? Well, various people have worked on it, and we now know that what you have to do is stick inside it something that repels gravitationally. That's pretty obvious. The walls need to repel each other gravitationally. And that means you have to have something with negative mass or negative energy. And in fact, and so you would say game's over. How can you have negative energy? And the answer is you can have it. And just for physicists, the Casimir vacuum and the squeezed vacuum. You have some squeezed vacuum. Do you have squeezed vacuum here in your new lab now, or you're just going to have it? There's a plan to have squeezed vacuum in the lab if they don't have it already. And so they're going to be making negative energy matter here, exotic matter. But the problem is, I'll tell you what the problem is in a moment. So can wormholes occur naturally in the real universe? The answer is almost certainly no. These are answers that a number of people have struggled to understand. And this is the bottom line after several decades of trying to understand it. Can wormholes be made by an advanced civilization? Possibly. It's quite possible, as John Wheeler told us, that down on very, very tiny scales of 10 to the minus 33 centimeters, called the Planck length, that there is a foam of tiny, tiny wormholes that's just bubbling and bubbling and bubbling quantum mechanically. And so you can imagine a very advanced civilization reaching down and grabbing one of these wormholes and enlarging it, making it big so you can travel through it. It's pure imagination. It's something you would do if you're a physicist when you're very, very drunk, to speculate about this. But I don't think it's totally out of the question. If you do have such a wormhole, can it be held open? The answer is probably not. And this is where a lot of work has been done, because it appears to require too large amounts of exotic matter, of gravitationally repelling matter, negative energy. But when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, sometimes spectacularly, so you don't take my pronouncements that you can't have wormholes too seriously. And I was willing to use it in the movie Interstellar. Finally, a few words about time travel. This is from a technical paper that I wrote with two students of mine, Mike Morris and Ulvi Yurtzi, in 1988. Suppose that my wife, Carol E. Winstein, has one mouth of a wormhole, and she's in this rocket ship, and I'm back home with the other mouth of the wormhole. And she goes out. She has a very advanced technology. She travels out close to the speed of light, turns around, and comes back. Now, there's something called the twins paradox, which says that she will age much less than I do. She may have aged a few hours or a few months, and I may have aged a few years when she goes out and comes back. And so I'm an old man, and she's still quite young, as we see each other looking through the external universe. But if we're holding hands, and I look at her wristwatch, and she looks at my wristwatch inside the wormhole, they have to tick at the same rate inside the wormhole. This is what the prediction is. And so looking through the wormhole, she sees me young, because she's young, and our watches have been ticking at the same rate. But looking out through the external space, she sees me old. So she returns back to Earth. And so these wormhole mouths are here almost side by side. And so all I need to do as an old man is go and enter that wormhole and go back and meet my younger self, because I can see my younger self through that wormhole mouth. Okay. So it's easy to turn a wormhole into a time machine if you have a wormhole. Well, not technologically easy, but relativity seems to allow it. The problem is that relativity, which seems to allow it, is not the only set of laws of physics that we have to deal with. We also have to deal with the quantum mechanical laws of physics. And quantum mechanical laws of physics, when you look at them, they seem to say that whenever any advanced civilization tries to build a time machine, the time machine will have a gigantic explosion at the moment it's turned on. And in this case of this particular time machine, the key issue is that if you imagine she's traveling back toward me, and there's a first moment when something could go down through the wormhole, out my wormhole, travel back, and return at the very moment that it started out, and so you have two of them. So these might be photons, particles of light, go through the wormhole and then back out the exterior region. You began with one photon, you now have two. They're the same photons, but they're side by side. Then the trip is made again, you now have four photons. They're the same photon, they're side by side. You have a huge burst of energy going through the wormhole at the moment that this wormhole turns into a time machine. Well, you can shield out photons, but you cannot shield out something called vacuum fluctuations. And these things, which are also called virtual photons, these things which play a huge role in modern physics and experimentally, manipulating this vacuum, which I'm not going to go into, is the key to making this squeezed stuff that is going to be made in the laboratory here that has negative energies. So these vacuum fluctuations can do this, and you can't shield them, and so there will inevitably be an explosion. And so I found this with a postdoc of mine in a calculation, and then some colleagues of mine, and here's a technical paper, did a far more rigorous calculation that showed the same kind of a thing, but not showing any details of the explosion. So I think this is incontrovertible that there is some sort of something really goes wrong the moment you make a time machine, try to make a time machine. But what we don't know is whether the explosion then is strong enough to destroy the wormhole. And Stephen Hawking was working on this at the same time as I was. Stephen is one of my closest friends, and we never collaborated together, but we worked at the same time on this problem, and we argued back and forth. And ultimately, we came to agree that we can't tell whether the explosion is strong enough to destroy the wormhole. Only the laws of quantum gravity, which we don't understand, know whether it will destroy the wormhole. The laws of quantum gravity govern the birth of the universe. They govern what goes on inside black holes. And they seem to govern whether or not time machines self-destruct. Stephen then proposed the chronology protection conjecture because he was so sure that the explosion is going to be totally destructive, that the time machines will always self-destruct when you turn them on, keeping the universe safe for historians. And that's his phrase in this technical paper, whose title is the chronology protection conjecture. So I was working on this at a period just before we got approval to construct LIGO. And when we got the approval to construct LIGO, I left this all behind because LIGO got very exciting. And I've not had a chance to return to it. But it's quite interesting that you see these weird kinds of things coming out of warped space-time, just like gravitational waves and black holes. So conclusions. When I was a student, there were speculations about the warp side of the universe. Today, 57 years later, we know a lot more. We have observed black holes. We have observed gravitational waves. We have a lot of observational evidence about the Big Bang. We doubt that wormholes exist and doubt that backward time travel is possible, but we're not absolutely sure. And in the future, I believe gravitational waves will reveal a great deal about the warped side of the universe. There will be enormous surprises of which we can't even dream today. Thank you.